Ladies and gentlemen, we are today very happy and privileged indeed to have with us Professor Chandra Wickramasinghe, who in my opinion is the greatest ever scientist to have come out of Sri Lanka. I know Chandra will blush when I say that, but that is my sincere opinion. Now, Chandra had a distinguished career in school and then got a first class in mathematics in the university in Colombo. And then he went to Cambridge, where his PhD thesis was, in fact, his project was supervised by none other than Sir Fred Hoyle, with whom he collaborated for the next 30 years. He was then awarded the DSc in mathematics from Cambridge several years later and became the youngest professor ever at the age of 34 in applied mathematics and physics in the University of Cardiff. Several years later, he started the Astrophysics Research Group in Cardiff, and in 2000 became the director of the Astrobiology Center there. He then retired in 2006 and then went to the University of Buckingham in 2011, where he also started the Center for Astrobiology Research, and where he is now. He is Professor of Astronomy and Astrobiology at the University of Buckingham currently. And he will again blush when I say this, but he has over 350 publications at the last count. And ladies and gentlemen, over 70 of those are in Nature. He is also the author of many books. And being the true polymath that he is an award-winning poet. He's published his poetry in leading journals where poetry is published usually. But his main contribution to Sri Lanka, in addition to all that he has done in astrobiology and astronomy, was that he was the founder director also of the Institute of Fundamental Studies. And for his scientific contributions, he's been proffered the title of Vidya Jyoti, and he is Vidya Jyoti Professor Chandra Wickramasinghe now. So Chandra, with that long introduction.
Thank you, Kuera.
Us know that, but I also forgot to tell the audience that you continue to be involved in the Ruhuna Astrobiology Center and Research Center, and you have an honorary professorship there as well.
As colleagues. So that's the situation. But I basically preferred always, even when I was a fellow at Jesus College, Cambridge, I preferred to work in my room at home, as you do, I think, Kuera.
Yes.
I see your bookshelf behind you. So I've always, and the joke was when I was at the Institute of Astronomy in Cambridge that I made my brief appearance at coffee time.
And the coffee was free.
Coffee was free, yeah.
Now, ladies and gentlemen, you will also realize that Chandra and I are very good friends. Our friendship has been forged over the last 30 years or so.
That's
we are very good family friends, and we got on very well together with each other. Now, Chandra, I want you to, at this point, introduce us to the concept of panspermia, which is perhaps the scientific contribution that you are best known for, together with Fred Hoyle, and let us know what your current status of knowledge is about panspermia.
Yeah. Okay. I'm glad to do that. In fact, I mean, the question really goes back to ancient Greece, to the 5th century BC, when they were talking about everything. They were inquiring about the nature of human beings, of human life, of love, and so on. And the beginnings of life is one of the prime concerns in many philosophical inquisitions that were taking place. So panspermia goes back to the 5th century, to pre-Socratic philosopher, a guy called Anaxagoras, who said that life has to be a cosmic phenomenon. Seeds of life, spermata in Greek, were supposedly, according to him, distributed right across the universe. So pans, sort of spanning everything, spermata, seeds. So panspermia was essentially a word that came from Anaxagoras. Those are the earliest sort of Western beginnings of panspermia. But the idea that life is universal, of course, goes back before that to ancient Babylonian, ancient Indian thoughts are also in that same direction. But I think we should really come back to what the world is now. If you look at the planet Earth, it sort of teems with life, life like you and me, and plants and animals and insects and so on. It's bacteria, viruses, they all, the Earth is teeming with life. But if you go back 4.5 billion years ago, the scene was totally different. The Earth was just being formed from impacts, from collisions of asteroids and comets, so little bits and pieces sort of banging into each other and forming the Earth. And there's hard evidence for that. Geologically and astronomically, we know that this is the way that planetary bodies form. So 4.5 billion years ago, the Earth had just formed. It was almost a complete ball, a sphere, but the surface was very, very hot. It was sort of really a cauldron of smoldering rocks and so on. So the first life now has been discovered to have been present in the rocks that are formed at this very early moment in time. Last year, the Australian outcrop of rocks in Jack Hills Mountains, in a sort of mountain range in Australia that goes back to 4.2 billion years, discovered relics of microbial life. So the first microbial life is really very ancient and is present on the Earth at a time when it should not be there really, because it's too hot. There could not have been any chemistry and so on. So I think this is the clearest indication empirically, experimentally, that the impacting asteroids and comets brought in the first life on the Earth. So this is a very, very striking sort of confirmation of panspermia at the very early moments in the life's history, in the Earth's history. Then as time goes on, of course, we know that life on Earth elaborated from simple bacteria to eukaryotes to multicelled life and so forth, all the way to plants, animals, you and me. But that process also took place in the midst of continuing collisions of comets and asteroids. The Earth is continually receiving stuff from comets from outside, sporadically in big lumps from time to time. We know that comets have hit the Earth, sometimes destroying life on Earth, sometimes, I think, bringing new life forms to Earth. And so this is a process that's been going on. So panspermia is an ongoing process in terms of bringing primitive life that can affect and influence the evolution of larger life forms. That's sort of basically the update on panspermia in terms of astronomy. And we also know now that there is very, very powerful evidence that comets have signs of bacteria in them. There was a comet, for instance, called Comet Lovejoy that was discovered 1.5 years ago. And this comet is sort of spewing out ethyl alcohol and a sugar, right, in vast quantities, equivalent to some 800 bottles of wine per second. This is going out. And people are puzzled as to how this is happening. It's clearly a process of fermentation happening underneath these ices of that comet. And then there were comets like the Rosetta Mission comet that was studied about 3 years ago, if the investigation finished 3 years ago. And then also there is tantalizing evidence of microbiology. So this is the general pattern that is emerging. And I think the evidence is growing almost by the day.
Chandra, that's very clear. But there are two questions that I want to ask you. The first is obviously, where did the life that was transported to the Earth originate from? That's number one. Where did life really originate? And number two, if you suggest that there is a transportation of these life forms across the vast reaches of space and the universe, how does life survive those horrible conditions? I may be
Well, I
asking a
think
very simple question, but
yeah, that's a very, very important question, and it has to be answered. I think the panspermia model that we have is that life is a truly cosmic phenomenon. The beginnings of life on Earth is just a non-starter. It could not have happened on the Earth, and the improbability of the organic molecules, the crucial molecules, either the amino acids for the proteins or the bases for DNA coming together in the appropriate fashion in order to start life is so exceedingly improbable. If you work out the probabilities of the assembly process leading to the simplest self-replicating life, you get sort of probabilities of 1 in 10 raised to the 3,000 or something. So it is virtually a miracle that the first life occurred anywhere, not just on the Earth, but anywhere. So I think one has to take that question of origins further and further back in time to maybe the beginnings of the universe itself, maybe kind of improbability. So the first origin is a mystery. It could be a miracle. It could. I think it is also entirely conceivable that there's an all-powerful deity that controls the universe, and there's no contradiction whatsoever with a generalized theological position as to how the first life originated. But once originated, right, these life forms in the form of microbes and viruses and bits and pieces that are components of life, they get into the first condensable objects, which are comets. Comets are everywhere in the universe, and there's 100 billion of these comets around our solar system. Once they're inside a comet, of course, they are protected essentially for an eternity, because it's on the surface, it's freeze-dried, it's frozen, it's very low temperatures, and there are domains within the comet with radioactive heat sources where the liquid domains and replication could take place from time to time. So this is the answer to the question how these microbes can survive for.
So they are protected in
they're
their
protected,
journey.
yeah,
Right,
yeah.
okay. Chandra,
But
the other question I want to ask you about is that in 2019, November 2019, you wrote that there is a pandemic about to happen in the near future. And lo and behold, we have the coronavirus pandemic.
Yeah.
Now, what made you think about a pandemic?
Well, I don't claim that I predicted the COVID-19.
Well, that's what your writing shows.
But okay, but yeah. what I did was what we did over many maybe a couple of decades, no, a few decades, is to try to correlate the emergence of pandemics with astronomical events, right? And the one astronomical event that appears to be very strongly correlated with pandemics now, as well as in the past, is the sunspot cycle. Right? The sunspot cycle there are several cycles in the sun, and sun's activity is variable, okay? And there's the 11-year cycle of sunspots where the sun is active and sort of there's a well-defined 11-year cycle. But over that cycle, there are bigger cycles, right? There was, for instance, there's a time in the 15th, 16th century when there was extremely low sunspot activity for many centuries, several centuries, a century and a half at least. And it is during that period that you had loads of pandemics, epidemics happening across the world, the Black Death and so forth. And in more recent times, the pandemics on the Earth were associated, we noticed this a while ago, with very low sunspot activities when the sun is not active. you have influenza pandemics happening, and so forth. So this is the correlation that we looked at, and we saw a striking correlation between low solar activity and the emergence of pandemics. And what low solar activity does when the sun is not active, it is not pushing out electrons at very high speed. When the sun is active, there are solar flares, right, and many sunspots on this, and these solar flares lead to the streams of electrons that reach the Earth's environment and maintain what is called a magnetosheath, a protective magnetic field around the Earth, which stops not only cosmic rays, it stops cosmic rays coming, very energetic cosmic rays, and it also stops viruses that can get out of comets, because these viruses are charged, and charged particles are inhibited from entering a magnetic field. So a magnetic field protects the Earth from cosmic rays as well as from ambient viruses from comets. And when the magnetic protection is lost, then we are open to the risk of pandemics. So this is what we noticed was happening as we approach 2019. We are approaching a very low period of solar activity, extremely low, maybe the lowest in 120 years. So Chinese collaborator and I spotted this first, and then we alerted a lot of other people, and we wrote this paper in Current Science saying that essentially a pandemic warning, that it will be prudent for health authorities to be alert to perhaps an impending pandemic of some kind. So that's the situation I can give at the moment.
So if you extend that argument, Chandra, person-to-person transmission is not a likely method of it propagating itself. Is that your view?
No. What happened, I think, in the case of COVID was the following: huge, maybe 10-meter sized icy cometary fragment containing trillions and trillions of these virions entered the Earth's atmosphere around sort of middle of October last year. It exploded, or it got disseminated in the Earth's, between the stratosphere and the troposphere. It was dispersed into what is called the northern jet stream, right? This is a stream of gas that goes around the Earth around 40 degrees latitude north, and it goes at a pretty high speed, 300 miles an hour or something. So it got into that, and whenever there is a turbulence in that, when there is a disturbance in that stream, then there's the stuff from the stream, particles from the stream can fall onto the ground for that. But once the virus comes from wherever it came from and gets into the community, then of course it's an infective agent. It spreads from person to person. So this is the rationale for all of the hospital protocols that you guys have taken, the PPE, the protection, the masks.
So does your theory of this coming from outer space make it imperative that we should be looking for other methods of preventing transmission? Or is there some modification that you would suggest to just social isolation, hand washing, and all the rest of it? Yeah. Or is there anything else we need to do in addition to all that?
No, I think that all that the measures that are being taken are very sensible and should not be relaxed until it becomes clear that people are not spreading that virus that came in the first place from outside. But how do you prevent it coming from outside? I don't think there's any way of preventing it from coming from outside. If it is coming, it's going to come. But what could be done in the future is to monitor the skies for our safety. Okay, I think there are technologies that are very well very advanced technologies that could, for instance, could have instant PCR detectors of virions ahead of their coming down to the earth, right? So we would perhaps know a year in advance that there is a virus that is likely to be pathogenic coming from space, and that will give us enough time to make preparations on ground.
You said years in advance. Is it possible to detect these molecules that far ahead?
It takes for the descent of a particle that is injected into the stratosphere to come to the ground, to ground level, could take up to 1-2 years. There could be a time lag of about 2 years, I think.
But you also think, Chandra, that during those 2 years, it's got the conditions appropriate for it to grow and replicate while they're doing so, while it's falling to earth.
No, it's freeze-dried. It's freeze-dried,
Okay.
so it's locked in its genome and so on. So until it comes to ground, until it finds an animal or human host, it is just a molecular entity. It's just an informational entity. So I think that's.
Chandra, one other question. Now, this particular SARS-CoV-2 virus has tremendous genetic and structural similarities to the previous SARS and MERS viruses. Now, if it is a de novo, or if it has a de novo origin, and has been lying in space for billions of years, freeze-dried in a comet, how do you explain that? How is that similarity, that close similarity, possible?
No, there's no evolution possible in the comet when it's frozen. It's just locked in its genome. So COVID-19, the virus that is now causing COVID-19 would be locked in its genome in that form. So you would have another fragment of a comet, right, with the other variants that are. So you get a huge range of variants that are distinct and in separate compartments of an icy bolide or something. So they are not. They would be related but separate entities.
Chandra, you've given us
capacity.
Yes, you've given us half an hour of your time, and that's more than I should be really pressuring you to do. But one final question: do you foresee any further pandemics at a time when the sunspot activity is low?
I think we are in for a series of pandemics in the next. Sorry to be so negative and pessimistic.
But that's the truth, isn't it?
I think that's the way I would see it, and it's the way that history tells things have happened for similar conditions prevailing. Right? As I said, the monde minimum was replete with pandemics, and the whole history of human civilization has been a succession of pandemics that clustered in time. They appeared over a certain maybe a few decades, then disappeared for long periods and reappeared and so on. And so that's something that we cannot avoid happening, but if we are prepared for it, then with all the modern technologies, all the biomedical resources that we have, maybe we can cope with future events a little better than we've been able to cope on this occasion.
Chandra, thank you very much for your time. And you've given us a fascinating view about what you're thinking about in terms of the cosmos and the pandemics that happen to us from time to time. And if you don't mind, we'll come back to you at another time to talk about these things and even more later on.
A pleasure, yeah.
Thank you very much, Chandra. We'll catch up with you later on. Thank you very much. Okay. Bye-bye.